So our session is called Off-Grid Mini-Grids, Case Studies and Industry Players Roundtable. So first of all, we would like to have a very quick round of survey with the people in the room. Yes, ladies and gentlemen, Dr. Lucas, if you can help us with that. We would like to start with a quick question. Okay, we are talking about mini grids. I know many people in the rooms have experience with mini grids. Yes, so we would like to ask, in your opinion, in a mini grid, photovoltaic mini grid, which one would be the most important, the most critical equipment? We are giving options. In a mini grid, the most critical equipment, is it the inverters or the transformers? Or option C, the PV modules, perhaps the batteries or the meters in a mini grid, or something else? Any other? Can we have a quick round with the audience, Dr. Lucas, to see if what do they think that the most critical equipment is in a mini grid? We have A, B, C, D, E, F. Other options? Ok, please.
Para acompanhar uma pergunta, qual é o equipamento mais importante ou crítico quando se trata de um sistema fotovoltaico mini-grid? Será a indução? Será os módulos fotovoltaicos? Será o banco ou a pilha de baterias? Serão os medidores, equipamentos de medição ou outro tipo de equipamento? Qual é o mais crítico? Ok, já temos resposta?
Yes, please.
Yeah. Oh, okay. Here. Yes, there is one answer now.
Yes,
eu acho
please.
que é a linha C.
Acha que é?
A linha C.
One answer from room 105. He says PV models is the most important.
PV models, the most critical. Okay, thank you. Any other opinion?
Alguma outra opinião? Yes, there is another opinion here.
D.
D.
Battery.
Another opinion is D, battery bank. That's second opinion.
Thank you.
Na sala de gente, por favor. Agora, answer from 105 again. Another answer.
B.
This one says B, transformers.
Muito obrigado. Thank you very much. Any other opinion?
Sala 205. Sala 205. Alguma opinião? Okay, we can proceed. No more opinions.
Okay, thank you very much. Thank you very much. In fact, in our opinion, everything is important, okay? So I am not surprised that we got 3 answers and the 3 were different and the 3 were right, okay? Any equipment can be critical, okay? In a mini grid, yes? Every single equipment, every component is important. Let's remember how a mini grid works. What are the main functions? Okay, we have first of all a generation side. Sometimes we call this the micro plant or the mini plant, where we do generate electricity with PV panels. We store electricity with batteries, and we convert electricity with the power conditioning equipment, charge controllers, inverters, etc. But then also we have a second part of the mini grid, the distribution, yeah, with the lines, okay, low voltage or sometimes medium voltage, before we can get to each consumer, each connection, yes, with the meter. And of course, all these different functions need to be controlled and monitored to be able to have data and to take decisions, okay, in a mini grid. People from FUNAI in the room, from EDM, I'm sure they know very, very well what we're talking about here. So today we are very lucky. We have in the room, in the session, specialists, colleagues that are going to tell us about storage, about power conditioning, and about monitoring, data collection and control, okay? Remember, we are following solar photovoltaic technology training course, yes? Yesterday, we looked at the introduction, overview, and we talked a little bit about the PV system generation, the modules. Today, we are focusing on the power conditioning and storage. This session, this afternoon, will have 6 parts. Now, we're doing the first part. I'm presenting the session. I am now going to introduce you, the industry experts today in the room. Then we will talk about power conditioning in mini grids with engineer Pablo Munoz from company Studer in Switzerland. Then we'll have a break. After the break, we'll discuss the battery technologies with engineer Santiago Antolin from Inventus Power. And then we will discuss control and monitoring systems and solutions for mini grids with engineer Joan Tarragó from Ferntech. And we'll have another break, okay? And finally, the last session today in the afternoon, we will put together different mini grid examples, and then we will have an open debate, some questions and answers. So I would ask you, if possible, when you have questions, if you can write them down, okay? And keep them for the debate at the end. Because I'm sure that some of the questions you might have, for instance, in session 2, eventually will be discussed, yeah? After, in any of the following sessions, okay? So please, we will ask you when you have questions, if you can kindly write them down, and then when we do the debate at the end, we can put everything together, okay? Because today we have a round table. So we have today with us 3 guest speakers. The first one is engineer Pablo Munoz. He's an engineer specialized in solar mini grids. So he's a full specialist on mini grids, okay? With over 12 years of experience in the sector, okay? He works at a Swiss company, Studer Innotech, that is a manufacturer of high quality inverters and solar charge controllers, okay? You have the website and you can check what this company does. Pablo has field experience working in different projects in African countries, in Chad, in Ghana, in Tanzania, Senegal, South Africa, okay? So he's a person that knows very well the story of mini grids, from the field to the manufacturing of equipment. We also have with us engineer Santiago Antolin. He's an expert with more than 15 years of activity in the areas of renewable energy, telecoms, and electromobility. He works at the company Inventus Power as field application engineer. He's specialist in the batteries, okay? And he's responsible for technical advice to customers and for the sales team in his company, okay? So he previously worked for Trojan Company. It's another very well-known battery manufacturer company, okay? With lots of projects and applications in Africa, okay? So we're very lucky also to have Santiago with us today. And finally, our third expert is Joan Tarragó. He also has a lot of experience in different industrial applications of renewable energies, energy efficiency, and also automation. Okay. His engineering experience includes many solar off-grid rural electrification projects in Africa, Latin America, and also in Europe. Yes, combining research, development activities, data analysis, and field work as well. Joan leads the business development area in a German company, Ferntech, okay, that they offer digital monitoring and control solutions for off-grid power systems, and they're very much specialized in the monitoring of mini-grids, okay? So let's please move on to the second part of today's session. I'm going to give the floor now to engineer Muñoz, Pablo Muñoz from Studer, that will share a presentation on power conditioning in mini-grids. So Pablo, please, I'm going to stop sharing. Thank you very much. And you can start with your presentation. I'll give you the floor. Thank you.
Thank you, Paul, for the introduction. Good afternoon, boa tarde, everyone. I would like to start with, well, as Paul was mentioning before, I was working in the field in various African countries. When I was in South Africa, I visited Mozambique. Unfortunately, I haven't been doing any project in Mozambique, but the visit was really great. We got up to Vilanculos, and it was really a very special place for us. So I'm really looking forward to have an opportunity to visit professionally as well Mozambique again. I will focus on the power conditioning in the mini grids. And if we start on what is the power conditioning for an off-grid system or for a mini-grid system, well, the power conditioning, in fact, is, we can say, is like the brain of the system, right? We will have the resources. I think I can use pointer. Huh? We have the resources, renewable energy resources, that will be introduced in the system handled by the power conditioning. We have the storage that will be also handled in order to be charged or discharged by the power conditioning. We have an alternative source like a generator that can be also used and managed by the power conditioning. And we have the monitoring side that will be also taking all the information from the power conditioning. And obviously, the most important thing, the loads, the electrical supply, that is also the interface with the final users. This is the same for a mini grid or for a standard PV project, okay? In terms of mini grid, what I would like to also point out is when we speak about mini grid, we speak about the most complete scenario for an off-grid system, because we need to combine several aspects in terms of the technology. But the technology is a technology that is available from the beginning of the solar and battery-based system projects and installations. So it's mature technology. The devices that we manufacture, for example, they have been manufactured for more than 10, 12 years. You will see other devices that even before were already manufactured. So the technology itself is existing. We have a lot of mini grids already running, and it's mature technology. This I would like to mention as always at the beginning of my presentations, because I have been also in the field. I have already experienced implementing pilot projects, and my personal humble and biased advice is when we start a program of mini grids in a place, that the pilot of the technology is not necessary. We can rely on the technology that is existing. Other thing is the rest of the components of the mini grid. And this is also important. The mini grid is also a very challenging project because it combines the generation, that is all this area that we see here, the power conditioning with the resources, the storage and so on. But we need to consider as well all the distribution. And we need to consider as well the end user connections, especially in places where there is no electricity before, where everything should be really implemented from scratch. So this is also very important to have on mind. When we look at mini grids, we don't need to only look at this part. Those two parts, they have also their importance, are very relevant for the project implementation. On top of this, a mini grid is not an standard infrastructure project. Okay, when we are installing or developing, implementing a mini grid, we are also servicing electricity. So we are just building a system that will provide a service, electricity, to the final users. And as this is a service, it has a technical component, that is how the electricity will reach the final users. But it's very important also to look at all the financial aspects, business model aspects to run this service. And we are dealing with users. So we need to have also the social aspects to be considered in order to interface with the final users. That's why a mini grid is really a challenging project, a very complete project. And well, I will focus on the technology and the power conditions. And when we look at the power conditioning, I would like to just establish what is what will be the main elements of the power conditioning in a system. This is for a standard system, applicable also for mini grids. Here I have put at the center of the image of my schema, of my schematics, I will have this is our battery inverter. It's called extender. We could use any other inverter for this. And then we will differentiate between DC and AC, okay? Direct current and AC current. The first element that I would say is the most relevant for an off-grid system is the load. The first thing that we need really to understand and to have on mind when we are defining an off-grid system is what will be the load profile that is required. Based on this demand, we will design the rest of the elements. Okay, very important to have how many energy we need, how much power, and what is the profile, whether we need it during the night or during the day. Another essential device is the battery. The battery, without battery, we don't have any autonomous system. So the battery is the central part for an off-grid system because it allows us to have the energy available for a stable supply of electricity. Okay. Another element is generator. This is an optional element. We can have a generator in the system. We can use this generator as a backup, or we can use also a generator for hybridize the system and maybe reduce our system cost. Even in a hybrid system like this, we could have a grid connection. We could have a grid connection that maybe is not always available, or maybe it's a weak grid that we cannot consume a lot of it, or maybe it's a weak grid that we need to combine and stabilize with our own energy. Then with the grid, we will have the possibility also to consume from the grid, but maybe also feed back into the grid, okay, any excess. And then the next element that is also important or critical in this kind of systems that we will see is the renewable energy resource. And I will focus on the solar, okay? The solar resource, we have two options to have it within our system. As you can see here, the battery is on DC. The inverter is the one doing from DC to AC. Okay, so all this area is on AC, all this area is on DC. So here we can have solar, our solar PV modules, we can have them. You know that the solar PV, they are supplying energy on DC. So we have here DC solar energy, and then we can have a DC-DC converter that is a solar charge controller that brings down from PV voltage to battery voltage, but still on DC. And this solar generation is coupled on DC, is on the DC bus coupled, and we move from DC to DC at battery voltage, okay? The other option to have solar in the system is to have our solar modules DC supply here with a solar inverter. So here we have a solar charge controller from DC to DC. In AC coupling, we have solar inverter from DC to AC. And then at the output of the solar inverter, we have AC. This solar production is coupled on the AC bus, okay? Now that we have introduced the possibilities, let me go back here. So I will do a quick comparison about what are the difference between having AC coupling or DC coupling in our system, okay? If we want to charge the battery, okay? If we want to charge the battery, our source of energy is the solar, and we need to bring the energy from the solar to the battery. Let me go back quickly here. So on the DC coupling, you see here from the solar to the battery, there is a very quick path, okay? On the AC coupling, from the solar, we have an DC-AC conversion and then an AC to DC conversion. So, sorry for this. Opa. So there is a longer path for this conversion. That's why when we are charging our battery from solar to the battery, we have the DC coupling option for the solar production. It has a very high efficiency. The energy that we take from the solar goes, almost all of it goes into the battery. If we use AC coupling for charging our battery, this efficiency is a little bit lower. It's still a very high efficiency, as you can see. On the other hand, if we want to make a direct use of the energy, if we have consumption during the day, the energy that we are producing from the solar, we can use it directly in our electricity consumption. So we don't need to go through the battery. In this case, the DC coupling, if you have still the schema on your mind, we need to go from the solar to DC-DC, from the DC through the inverter to the AC loads, okay? So the efficiency of this conversion is a little bit lower. And the AC coupling option is much more, or it has a higher efficiency because from solar through the solar inverter, we get directly into the loads. This is very important also to understand which type of design do I need for my mini grid, depending on how I use the mini grid, depending on my demand, depending on the energy that I will require. That's why I was saying that the most important element for designing a system is the loads, okay? So maybe with this kind of comparison, we can say that if we have mostly night consumption, we will need to use the solar energy through the battery because we consume during the night, not when the sun is there. Then the best architecture will be to have DC coupling. However, if we have a daily consumption, the best architecture, the most efficient architecture will be on AC coupling. Is there anyone better than another? Not necessarily. We need to adapt to what is required for the demand. This was a kind of summary of what is the impact of the load profile, right? Now we will look at the battery. And again, what should be my battery for my mini grid system? Well, the battery depends on the autonomy that we want to have. But also the battery depends on the load, again, that we need to supply, right? That's why it's also very important, the load. Well, when we define the battery autonomy, it will really define what is the battery size and capacity that we will require, according also to the solar power and the consumptions that we have available. Let me give you some examples in some graphs. This is a daily graph from midnight to 24 hours midnight. So we have the orange is, let me say that way. The full profile is the demand that our system will have, okay? The orange profile is the energy that we will need to have it, we will need to supply our system, we will need from the battery. And the yellow one is the energy that we can supply from the solar, okay? In this case, we have 3 times solar and 1 time battery. So we have a small battery and kind of big solar field. The same profile, the same curve. If we have a bigger battery, but a small solar, then because the solar is small, we need the battery to supply also during the day. So then we need to increase our battery capacity with the same, exactly the same load. On the other hand, look at here, this profile is different. This profile is heavily focused on night consumption. So our peak of demand is during the night. So here, even for a standard design, we will need at least double of the battery than on the previous one, because here we have much more night consumption. Okay, the day consumption is lower, so yeah, in solar we are in the middle. However, with the same profile, if we still have less PV production, we need to increase our battery a lot. So as you can see, we cannot define what is my best battery for this system. We need to know what is the load that we have available, what is the autonomy that we need to have, and also what is the solar resource that I have available. And I agree with the lady that was answering to the question. From my point of view, the battery is one of the most critical devices of the system, because we need to take care of the battery in order to make sure that the lifetime is there, okay? And then is a heavy element of the system. So the goal of the design should be just to maximize the battery lifetime, so the system lifetime. Another element that I was mentioning before is a generator. And a generator could be used as a backup or as an additional source of energy. I know that we want to kill the diesel. We are all looking to use as much renewable energy as we have available and reduce the pollution and the contamination, right? This is our own goal for all the projects. However, the generator, depending on the demand for pure off-grid systems, when we have only solar resource available, which is limited, the generator can help to influence the system efficiency. And let me explain. I take the same graph as before, right? We have not so much solar energy, so we need a big battery, because we need to cover with the battery, we need to cover some parts of the daily consumption. What happens if in this case we cannot have more solar power for whatever reason, but we could have a generator? If we have a generator, this generator can help us to reduce this peak and this peak. So the use of generator will help us to reduce our battery and to keep the existing battery in a more efficient behavior. So this will maximize the system lifetime. So this is an option to be considered, right? On this other hand, we have this night profile, so we need to rely again a lot on the batteries. If we will have a generator available, we could use the generator for the peaks, for the peak consumption. In this case, this generator will help us to reduce our battery, to reduce also our power system power during the sizing and the dimensioning. So the generator in both cases will help us to not oversize our system. Okay, so this is a tool that can be used according to project requirements, to context requirements, and so on. Now that I have already discussed a bit about the theory, I would like to share also with you some of the case studies, some of the field experience that we were mentioning before. So I will share with you this nice project that we did in Tanzania. It was a mini grid in the north region of Tanzania. This is the region, it's called Tanga region, is where the tea plantations are grown. So it's a place where there is a lot of tea agriculture. This is a very interesting project because it was one of the first projects, the first mini grids to be developed privately. So there is a local developer, the local developer is Ensol, that was implementing the mini grid. Ensol collaborated with TTA, Trama Tecnometal. This is the engineering company where I was working before joining Studer. That's why when I participate in this project, I was just as a TTA field engineer. And then, well, Ensol also just got applied for funds for the EEP program, for UNDP, and so on. And they implemented this mini grid. Okay, so they arrived to the community, and they spoke with the community. We are going to bring a mini grid here. They will do an estimation of the demand, and based on this, we were preparing this this design. As you can see here, there are Studer devices, the converters, and the charge controllers. Okay, this is an example of the PV field that was on top of a pergola structure with the technical house below that to be protected and covered. This is the power conditioning room with the inverters and the solar charge controller. And this is a picture of the distribution line. As I was saying, very important elements of the system. You see here a picture of the community. So there is like mountains, some hills on there. So distribution line, as you could see, has an impact in terms of installation, also project cost. The specifications of this project is a mini grid of about almost 50 kilowatt of solar power. In terms of inverter power, we are at 32 kilowatts. We have a big battery bank with 265 kilowatt hour. A long distribution line, however, in low voltage, and the project, the mini grid was supplying also some street lighting for the community and some users. During the commissioning, there were 30 users connected. The goal of the project was to connect 150. That was the demand that was estimated, and nowadays I think they are. The last time I was checking, they had 145 users connected to the mini grid. Okay. This project was also awarded with this Alliance for Rural Electrification Award of the best project of the year in 2017. What we were looking as technical aspects, what was considered for the power conditioning. So very important, the local capacity, how we build the systems in in the field, we are going to build with the local people that will be later on managing. So this is very important because the people that will take care of the system, they will learn about the system from the beginning. Also, a lot of work for the preparation, for the design following the flow of the energy, labeling, and so on. Very important things to have on mind. When we speak about O&M, O&M is critical and for a mini grid. Mini grid, we don't need to look only, we don't have to look only at the installation side. We need to look also at the O&M, what will be during the operation of the system. In these projects, we were structuring the O&M in 3 levels. The first level was a local management level that were doing the daily maintenance tasks, okay? Second level were the specialized technicians. They were the ones that could intervene if something happens, or that they do the corrective, the preventive maintenance, the program preventive maintenance, but which requires a technical intervention, right? And then we will have even a third level, which is more management level, like at operator or service agent level. This is to follow up technically and business of the mini grid service. Well, Joan will deep a little bit more. We'll go deeper on these O&M aspects. But what I want to point out here is that it's very important for this level 2 and level 3 to have people prepared. And at the Studer, we have this program of Studer training where we invite people that work with our devices. We invite them to our factory for a training in order to be qualified to do the O&M level 2 and level 3 of our devices. This could be maybe interesting for EDM, FUNAE representative sometimes to be well, to be discussed and see whether it could fit and could be of interest. I think if you consider to do mini grids, it will be a good thing to do. So just a summary on mini grid and the technical aspects. Solar DC couple. Why is this important? It's because we'll make sure we'll protect the battery. We'll make sure that our battery is charged because the battery is the central element of our energy supply. Generator. Is there a generator? What is the role of the generator? Is it worth it to make a generator to have a bigger role? So when is it available to help us keep our system efficiency higher? Solar AC coupling. Solar AC coupling, very important for daily consumption and maybe, for example, where we are expanding our mini grid, when we have an industrial consumer that joins the mini grid and at a later stage, we could have a solar AC coupled system for this user to help on the supply of it. And then the last aspect, distribution line. The distribution line could represent even up to 50% of the total mini grid initial cost. So very important to have it on mind. And in order to have technology to add to this distribution line issue, I would like to introduce you now another concept, and it's the concept of a distributed mini grid. Okay. And for using or for speaking about this mini grid, I will use another case study. This one is in Switzerland, where we are sitting close to the factory, to our factory where we manufacture our devices. This is a mini grid. Well, I will just launch this to set up the context. Imagine that you are at the heart of the Alps at about 1,700 meters height. This is a community that it was used in the past for the people having the cows in the valley. They were climbing up in summer for the cows to be more fresh and to have more grass for eating. Nowadays, this is used more like a leisure house, holiday house for the people to do the weekend or the summer. In this community, we have 32 houses. They were all equipped with small solar systems, individual solar systems, solar home systems. They are occupied during the summer and on weekends because the access is very difficult, and in winter there is no access, the road is closed and is covered by 2 or 3 meters of snow. So this is just to set up the context of on when we do usually implement mini grids in places with really difficult access where the main grid cannot reach, right? So this community, they were rebuilding the distribution of the water, and they thought, maybe we can ask the grid operator to connect ourselves so we can have the grid in our houses. The high voltage grid is not so far in this valley that you can see here, but the grid operator said that it was impossible and too costly. So they came to us because they know that we do off-grid system. In this case, we analyze, okay, what we can do, what is available here. This project was implemented 8 years ago, just for setting up the context. We said, okay, what are the possibilities? We can have individual installations, so everyone has its own individual system, or we can have a central system where we have a central infrastructure that is shared between all of them. We were just checking what is the advantages and disadvantages. So we like it from the individual that is independent, it can be adapted to the user, that is very flexible. On the contrary, the individual setups have fixed power and fixed amount of energy, and the batteries are suffering because we rely mostly on the single battery that this system has. However, when we look at a central system, we see as the advantages is that we share the infrastructure cost of a central system between the users. We have a centralized maintenance and management, and is closer to the grid in terms of business model. This is also sometimes helping. On the other hand, some disadvantages is dependent on the central system. So we depend on some infrastructure. There is a full blackout during maintenance or during an issue. The fixed system is size, the size is fixed in the system at the beginning, so it's not so flexible. And then we have an infrastructure to put in place, right? So then we said, okay, guys, let's do better than this. We want to do something that takes the advantages of the two solutions, but have a full new solution that is better than the existing possibilities. We took the solar home system concept where a user has its own backup energy that can be used. And we say, let's add to this backup, let's add it an excess and shortage. Let's add a value of, or a possibility of consuming more energy or sharing the excess of energy with the rest. The idea is share the benefits and not the problems, right? So we came to a solution that was, we interconnect the individual systems. If we interconnect the individual systems, they are still having their own backup energy, but when they are connected, they can consume from the mini grid and they can feed into the mini grid. This is the mini grid with all the systems interconnected in a grid, in a mini grid. We have one player that plays the coordinator role. This is the voltage source inverter, we call it, is because it's the one that is supplying the voltage and the frequency for the rest of the grid. Okay, the rest of the users, they connect with the mini grid and they act as current source inverters. They exchange current with the mini grid. Okay, but they synchronize with the mini grid that was set up by the coordinator. We can have a producer, so a user that is only producing and injecting, feeding into the mini grid. We can have a consumer, which is only consuming energy from the mini grid, and we could have a prosumer that can consume when its own production is not enough, and it can feed into the grid when its production is bigger than the consumption. This was very interesting as a concept for us, okay? How is this working? This is working thanks to the mini grid function that was implemented by us. And we needed to have some function that set up the rules in order to ensure that there is the security on the mini grid and there is equity in terms of the energy and power exchange between the users. For that, we were using a mini grid function based on the frequency control. And let me explain how this was working. I was saying that the coordinator is the one that set up the voltage and the frequency of the mini grid. In this case, he will set the frequency at 50 Hertz, right? Well, we were playing with the frequency. So the coordinator, when the state of energy in the mini grid was very good, we had overproduction, then the coordinator just set the frequency high. So all the rest, they see, there is high frequency, so that means there is a lot of energy to consume, okay? This is the same function that we use for working with solar inverters, the same function that the solar inverters use to reduce their power when the grid, for example, is already full or they don't need more energy to be fed. On the other hand, the coordinator makes the opposite when there is low state of energy. So if our mini grid is running low of energy, then the coordinator set the frequency of the energy at a low frequency, 48 Hertz. In this case, the others, they know, oh, now we need to supply, we need to contribute to the mini grid. We cannot consume from the mini grid because there is no energy available. This was very, very interesting function to implement. And then the mini grid function is the one, the coordinator doing that. What does the distributed inverters doing? They look at the frequency, and based on that frequency of the central mini grid, they compare with their own battery, and they say, oh, I have more energy than the central, or I have less energy than the central. And based on this, they know that they can consume or they cannot consume, they can fit into the grid or they cannot fit into the grid. The mini grid is operating since 2011. The use of generator was really, really reduced. So this exchange of energy was helping to users to share their excess of energy to other users that they were running short. One very important aspect is no more deep discharge of the batteries in winter. As you could see here in winter, with all the snow and everything, almost all the PV modules were covered by snow. So only the small PV modules that they are on the facade, they still producing. They keep the battery up to a certain level. Now, as they are all interconnected, even if you don't have your PV modules, your small PV modules, if one of the users have, they can share with the others in order to avoid the deep discharge of the battery. And then Santiago will explain later what will happen when we have a full deep discharge of the battery. So the main advantages of this solution is that it's very easy, very flexible to upgrade with no power limitation. In this case, for you to have the numbers, the coordinator unit was 6 kilowatt or is 6 kilowatt. In distributed power, we have 36. We have 6 times the central, the coordinator power distributed. In case of problem, only the user in question is impacted. And one interesting thing is that every user could play the central inverter role. It's only configuration. So if the central inverter has a problem, another can take over and play the central inverter role. Very flexible to integrate new users, whether producer, consumer, or prosumer. The energy distribution is done with very reduced cable size. So for distribution line, it's very interesting because we are not bringing power to all the users. Every user has or every system has its own power. They need only to exchange energy. This helps us for the distribution. Every user remains independent and autonomous. They can do whatever they want with their systems. There is no external communication. This is very important. The frequency of the line is the only communication that is available. And based on the frequency, very robust, very reliable. The rest of the system, they know how to do it. So we don't know computers, routers, communication, and so on. Very robust, very reliable. We know from being manufacturers of battery-based system for more than 30 years now, how reliability is important for the off-grid system. And then the perspective. This project was just to prove the technology. There is the business model to be integrated on it. There is new technology like lithium battery. Santiago will also go further on it, but new technology can help us to be more flexible even in the way we exchange energy. It's already compatible with solar inverters, with other sources, with meters. So very interesting perspective for this kind of distributed mini grid concept. And I get to the end, to my last part of the presentation. The power conditioning and the battery management. We need to manage the battery. And the battery, as I was saying before, is the central element of our off-grid system. Without the battery, the rest is not working, okay? We, as manufacturers or high quality manufacturers, we have always been focusing on adapting as much as possible to the battery requirements. So our devices, they can configure, they can manage every battery type to adapt to the battery profile as much as possible. This is very important to ensure battery lifetime and then system of lifetime. And the battery lifetime and system lifetime is not only the lifetime of the devices itself, is cost of the project at the end of the life. So higher cost equipment costs more at the beginning, but makes you to spend less during the project operation. This is very important. So in terms of battery, with our devices, we can deal with lead acid batteries, all type of lead acid, open, gel, AGM, with different technologies batteries, chemical batteries, so to say, and also with lithium batteries that are the new technology that is coming and is already established. Well, there is a lot of experience already on the field, but since the last 3-4 couple of years. When we deal with lithium battery, is different than the rest of the batteries. The rest of the batteries, the power conditioning element is the one that is doing the battery regulation, battery charge and battery discharge. However, for lithium, the lithium batteries, they have a battery management system, BMS, integrated in the battery. So they are, so to say, smart batteries already. In this case, there is no need for the extender or for the inverters or the charge controllers to do the management of the battery. This is done by the BMS. What we need to do is communicate with this BMS. So what we needed to do in order to adapt our devices for lithium is just to develop this communication bridge. So we have all our devices communicated with the BMS. The BMS is setting up here what are the battery requirements, what is the maximum charge, what is the target voltage, and so on. And the rest of the devices, they will follow what the BMS is saying. This was one of the challenges for manufacturers, just to adapt to new market trends and market situations. And what is interesting with the BMS and the lithium batteries is that we have all the information from the battery. So we can play also with SOC for the configuration. In our case, we developed this CAN bridge communication module that has the BMS option to speak with the BMS, but also communication with the standard. Very complicated because every battery has its own protocol. So what we did in this case, we designed a multi-protocol concept where with deep switch and jumpers, we can adapt to the configuration of every protocol of the batteries that are qualified. Okay. Well, And then if we look at the mini grids at the previous schema with the focus on lithium batteries, the importance of the DC coupling compared to AC coupling is that DC coupling is in direct communication with the BMS as well. AC coupling is a little bit slower on the frequency control because it's through this inverter that is controlled, just for you to know. And well, just to give you an idea of our company and what we do, Swiss manufacturer of battery inverters and charge controllers, we have our factory in Sion in Switzerland, and we have all the process at our factory in Sion. We have more than 30 years of experience, 2 gigawatts installed. We have a lot of weight on R&D. We are a lot of devices installed worldwide and a big network of student partners. To look at Mozambique, Mozambique is a country that is not so developed from our side. It's mostly touched by our South African partners. And then, yeah, quality means that off-grid projects are difficult. We started in Switzerland with difficult installations at 3 meters high here in the Alps. We have some projects at 4,000 meters in Chile, and even one system that is supplying a telecom installation in Peru at 5,000 meters. So reliable products. And then reliability means also lifetime. And I wanted to show that we have still devices that are working. This is the first series that we were producing, and we have devices that are still running. That is the importance of the quality and the manufacturing process. The summary of the products that we manufacture: simple battery inverter, hybrid inverter, where we can have DC to AC and AC to DC for charging batteries, the solar charge controllers, and we are also working on a new generation of smart inverter chargers that will be coming next year. It's called Next. And then, well, every type of application. We know off-grid projects are difficult. We need to adapt to a specific difficult context. So the devices will be flexible, configurable to really work in any type of project, mini grid being one of the most challenging applications to be done. So, muito obrigado. I hope I am still on time. Thank you for your time. Muito obrigado. And then, yeah, we continue from here.
Okay, thank you, Carlos. Okay, so thank you, everybody. Now let's move on to the next presentation. If you remember from our, let's see, from our program. Sorry, let me just go back to the program. We were here in the break. Okay, now our next session, our next speech will be on battery technologies with engineer Santiago Antolin from Inventus Power. So Santi, when you want, the floor is yours. Please share your presentation, and
yes,
you have some 20 minutes. Thank you.
All right. Thank you very much, Paul. Let me share the screen here. Is it sharing something or?
Yes, you can put it in presentation mode if you want. Okay. I think that's fine. Carlos, in the room, is this fine?
It is fine. We can hear you, we can read it properly. It's okay.
Thank you.
All right. Perfect. So thank you very much. And yeah, good afternoon. Boa tarde. My name is Santiago Antolin, and I'm the field application engineer for Inventus Power, which is a lithium ion battery manufacturer from the US. And today, in today's speech, I'm going to talk about energy storage for renewable energy, and specifically for off-grid mini grids. So let's get started, because Paul just booked me for 20 minutes on the most important and critical topic, which is the batteries. So I'm gonna give you an overview of what are the batteries mostly used in off-grid and poor grid applications. But let me start explaining a little bit of where we find batteries. Actually, batteries are now everywhere. No? From robots, we can find batteries in robots, in heavy equipment, in electrical vehicles, especially now. It's a trend. It's a big topic, especially in Europe. With all the electrical vehicles and trying to reduce the carbon the carbon dioxide which is exhausted to the atmosphere. So we can find batteries everywhere. But the most actually interesting application to me, it's to install and to use batteries in renewable energy, because in most of the other let's say applications, still the power generation is made out of combustion engines or made out of coal power plants. But the focus of renewable energy is very, very important for preserving the nature and preserving our earth to our kids and kids of the kids. So I think we're going to talk about renewable energies and batteries that come along together. Actually, both topics for a long future, hopefully. So, okay, let's get started. What is a battery? And actually, I think Paul is going to introduce you to this amazing topic of batteries in another session. But I'm going to just give you a very short overview of what is a battery and what batteries do we find for off-grid applications and mini-grids. So a battery is actually an electrochemical device, okay, and it stores electric energy with some chemical reactions happening inside. You don't see, so when you see a battery, you see just a box, but actually inside there's a chemical reaction happening all the time, which at the end it results on energy storage. It's like a miracle. But let's go a little bit deep into what a battery is. So a battery, it's actually it's made out of different components. Okay, you can see in the picture. It's made of two electrodes, the positive and the negative. The positive, for instance, in a lead acid battery is lead dioxide. In a lithium battery, it's made of different chemistries. For instance, iron phosphate, nickel, cobalt, aluminum, nickel, manganese, cobalt. So there are different types of cathodes out there. The anode, which is the negative electrode, in a lead acid battery is made of lead. In a lithium ion battery, it's made out of graphite mostly. Okay, so the anode and the cathode, both electrodes, should have a separator in between. This separator actually acts as to separate both electrodes. Otherwise, we would have a short circuit, and if we have a short circuit, then the battery it's completely dead. So that's why the separator has to separate very well. Has to be a very hard separator, not to break after many cycles. All right. In a lead acid battery, this separator is made out of rubber with some and also could be as well fiberglass. In a lithium battery, it's made of polyolefin, which is a type of polymer. And everything is actually submerged by electrolyte. So the electrolyte is that could be liquid or could be in form of a gel. You will see later some differences. The electrolyte, it's the way that the ions are actually transfer from the negative to the positive when we discharge the battery, or vice versa, from the positive to the negative when we charge the battery. So what happens when the battery is discharged? That means that we extract energy out of the battery, electric energy, electricity, and there is a current flowing from the positive to the negative, all right? And yeah, it power up the load. So remember, the electrons are going to, the electrons flow are going on the opposite way of the current, okay? The current is from positive to negative. The electrons are moving from negative to positive. And to counterweight that electron flow, the ions, which are the positive particles, are moving from the negative to the positive. All right, in a lithium battery, the ions are the lithium molecules, the lithium atoms. All right. And in a lead acid battery, actually, it's the hydrogen ions. All right. So you can see that a lithium battery and a lead acid battery, actually, it's a pretty similar, let's say, chemical reaction. It's just different components, different materials. All right. So let's go back. Let's go to the batteries that we can find in the market for off-grid and pure grid applications. And I'm just gonna focus on these three types of batteries because are the most common batteries out there. And you can find other types like nickel cadmium, nickel metal hydride, zinc, but these are, I wouldn't say very old. I mean, these are like old technologies, but also lead acid is a very old technologies. So they are not as used as these three types. No. So the most used actually so far it's the fluoride lead acid, FLA. The fluoride lead acid, it's a lead acid battery, of course, and it has a liquid electrolyte. So the electrolyte is a mixture of water and acid sulfuric. And you can actually easily know that it's a fluoride battery because it has a cap on top of the battery. So that cap, you need to take it out to top up with water. Okay, so it requires maintenance. Specifically, you have to top up with distilled water from time to time, because these batteries gas. So they exhaust gas during charging, especially, and they lose water. So you have to regularly maintain topping up with distilled water. We have, there are different types of fluoride lead acid, what we call tubular technology or flat plate technology, with advantages and disadvantages from each of the types. Most used, especially in off-grid applications, is what we call the OPZS. The OPZS is a tubular fluoride lead acid battery. All right, so probably you've heard about this technology. Then the second type is what we call VRLA, valve regulated lead acid. It's also a lead acid batteries, lead acid chemistry, but they are sealed batteries. So you could recognize easily because they don't have a cap on top of the battery, and you cannot open. So you don't need to maintain. You don't need to top up with water. So there are basically three types of VRLA batteries: the gel ones, which could be either tubular plate or flat plate. The gel means that the electrolyte is mixed with silica and it forms a gelified substance. So that's why the name of gel. It's like a gel pudding, let's say. And then there are also available what we call AGM. The AGM stands for absorbed glass mat, and is the type of separator that uses this type of batteries. So here you can see an AGM battery from Trojan Solar AGM batteries. And well, basically the advantage against the fluoride lead acid is that you don't need to maintain at all these batteries. So you just put it in the install it in the system, and you almost forget. The drawbacks is that at very high temperatures they might dry, especially if you don't use the correct charging settings. All right. And then the third option that it's mostly coming now, it's with lithium batteries. So here you see the Inventus Power lithium batteries packs. Again, there are different chemistries out there. So the LFP, the iron phosphate batteries, are the most used because are the most safe and provide most cycles out of it. It's completely maintenance free, so you don't need to top up with water, and are completely sealed. So yeah, but you will see that on contrary to fluted or VLA batteries, lithium batteries has other advantages and disadvantages, especially on costs. No, but you will see later on some other examples. So move on. What type of systems we find batteries? So basically we can differentiate between off-grid systems, the systems where there's no power grid, completely isolated, very remote places where we need the battery to deliver energy to the loads 24/7. For instance, solar home systems. These are small systems with 2-3 panels, PV panels, charge controller, a battery, and maybe a small inverter, or even without inverter for the DC loads. For instance, some LED loads, or maybe just a fan or whatever. So very small systems. In this type of solar home systems, mainly are used fluted lead acid batteries or VRLA, what we call AGM batteries, because they don't the user who are normally non-skilled users, they don't need to maintain the battery at all. Then the second type of off-grid systems are the rural off-grid houses, or a little bit bigger commercial houses or buildings where there's the system is a little bit large, and for instance, like 10 PV panels, charge controller, and inverter to the AC loads. And the batteries mostly used are VRLA batteries, again, AGM, tubular OPZV, which is the tubular gel battery, and also lithium batteries in an extent. And then microgrids or rural communities, mini grids, what we have, what Pablo was explaining before. We find also lithium batteries and mainly VRLA batteries such as OPZV or large AGM batteries as well. And the second category of energy storage is what we call inverter backup, which is well, these are the systems installed in a very unreliable grid where there is blackouts for certain periods of time during the day. So there, the battery will deliver energy during these blackouts, and yeah, typically commercial or industrial systems with AGM or VRLA or also lithium batteries are used. All right, so what are the challenges that we faced in off-grid poor grid applications? Well, one of the main challenge actually it's transportation, logistics. As Pablo was saying, the mini grid systems are installed in a very remote places where there is no grid at all. So the extension of the power grid, utility grid, is super costly. So these are really remote places. So you need to think in advance how you're going to transport all your material to that location. So that's why we're gonna think about systems and components that can be transported. So we're gonna check dimensions. We're gonna check weight of the components. So we're not gonna bring super heavy material components, batteries, to very remote places, because that's going to cost a lot, and it's gonna be really difficult. So transportation it's one thing. Modularity as well. So the components should be modular. In case there is a failure, in case there is an issue, we can just replace the component easily, and we can find we can also even stock some spare parts for those critical components, for instance. And the components should be very reliable and do not have any environmental impact. Okay, so and we need to think about, and this is very, very important, how at the end of the life of the system, of the project, how we're gonna actually recover all the components and recycle them. Okay, so from batteries, not only for batteries, but also for PV panels, for the other conversion power conversion equipments. No? So check for quality. Always check for high quality components, and also check for warranty conditions. What the manufacturers offer you as warranty, and take into account to have warranty periods that are accordingly to the experience of the company. So you might have seen companies offering 5 years warranty when the company has not even have any experience on the field for more than 2 or 3 years. So check these details. And local OEM capabilities. So we need to train. We need to give training to the workers that are going to do the operation and the maintenance, to easily and to successfully do troubleshooting in case there should be some troubleshooting, in case they have to replace anything, to do preventive maintenance as well, and corrective maintenance. So it's very, very important, local OEM capabilities. So I've created this chart just to explain a little bit the differences of each technology. So you have fluided lead acid, VRLA, and lithium-ion batteries. In terms of chemistry, all right, so we talk about this. In terms of maintenance, we also talk about this. So the fluided lead acid needs an electrolyte maintenance, while VRLA and lithium-ion does not need any electrolyte maintenance. Thought we should have everything clean. So there is some maintenance at the end. So we need to maintain everything clean. The terminals out of corrosion, check temperatures, etc. In terms of safety, obviously fluided lead acid has a concern on the acid. So as these are open batteries, there could be some spills of acid around. So there's some acid concern. VRLA, these are sealed batteries, so pretty safe batteries. And lithium-ion batteries, also very good. Thought the batteries needs a BMS, and this was already introduced by Pablo. The BMS is the battery management system, which is the brain of the battery. Actually, it's going to control everything. So it's going to protect the battery from over voltage, high temperatures, very low temperatures, high discharge currents, high charge currents. So the BMS, it's really needed on a lithium-ion battery, because otherwise the battery could run into a thermal issues. And I think you've seen everywhere how lithium batteries explode. No, so that's because the BMS has to be very, very high quality, with high quality components, and yeah, you should rely on a very good BMS. And I'm gonna go quick here. Specific energy, the best actually is the lithium-ion batteries. So for less kilograms, you have much more energy out of it. All right, so you need less space to have the same energy. All right, as a fluided lead acid. So that's why you've seen huge banks of fluided lead acid batteries, while with lithium you can actually reduce the battery compartment thanks to this specific energy number. Life cycles. So life cycles means that the life of the battery. All right. So one cycle typically it's one charge and one discharge. And fluoride lead acid provides 600 cycles at 50% of discharge. That means that if we discharge the battery to half, the battery is gonna have 600 cycles. And you see, for instance, for lithium-ion batteries, you can fully discharge the battery, almost full discharge the battery, while they're gonna have much higher life cycle. All right. In terms of costs, the less expensive batteries actually are the fluoride lead acid. As in contrary with the lithium-ion batteries, these are a little bit more expensive on initial cost, let's say capex costs, but the cost of ownership, the cost over the life of the project, it's much lower on lithium batteries because you don't need to replace the batteries every 2-3 years. So the batteries last for the whole project life on the lithium batteries. That's why the cost of ownership, the cost of the project over the life of the project, it's much lower with lithium batteries. That's why we found it in mini grids, in industrial applications, in in huge battery banks like container loads, container solutions for utility grid regulation, etc. All right. So very quick because I'm over time. So just a quick reminder here. So the battery safety. So when we designed a battery system, we need to take into account different parameters to make it super safe. So we can have issues due to electrical things, like the hazards, like short circuits, temperature control. It's very important. So the batteries work at 20-25 degrees Celsius. This is their best temperature to work with, to perform. So higher temperatures than 25 degrees Celsius, then you start reducing the life of the battery, the performance of the battery. So we need to really control the temperature of the battery room. Charge and discharge control as well, installation and maintenance. So I've created here a very quick checklist of what to think about when we design a battery system, an off-grid system. So take into account the breakers. These are really important. Not only the AC breakers, but also the DC breakers. So you're gonna have breakers on the DC side, from the PV to the charge controller, from the charge controller to the batteries, from the batteries to the inverter, and all should be rated accordingly. All right. Similar to the wiring section. So the batteries are gonna draw high currents. So we're gonna need to properly dimension the wiring sections and also accordingly to the local regulations. So it might not be the same regulations in Mozambique than in, for instance, in Spain or in Germany. All right. So you need to check also low electrical regulations. All right. Temperature range. So during the year, so might be some seasons are higher temperatures, lower temperatures. How we gonna compensate higher temperatures? Maybe with better ventilation or even with air cons. Thought in the mini grids it's not really recommended. Charging set points, as Pablo was telling before, it's super important to really charge the batteries with the correct algorithms, with the correct charging settings. Otherwise, we run into bad performance. And also the low voltage disconnection. So you need to set up also a low voltage disconnection in order not to full discharge the battery. So what happens if you continuously deep discharge a lead acid battery? The lead acid battery is gonna start to sulfate, and it's gonna make a reduction of the life, all right, as well. So less cycles out of it. Battery management system should be accordingly to for the lithium batteries, and should communicate with the power conversion equipment, as Pablo was telling us in the last slides. Location and position of the batteries as well. So we're gonna install batteries with some distance in between them, so that there is some air flowing between the battery cells and the thermal. So it's a better thermal condition to overall, as well as the ventilation. So you can see here a picture of a non-ventilated area where these batteries got a lot of hydrogen exhausted, and the hydrogen with high concentrations could be explosive. So we need to remove that hydrogen from the battery room. So we need to think about proper ventilation. Tools needed. We cannot use non-insulated tools. So we're gonna always use insulated tools. And last but not least, skilled workers. Again, we need to train people that are going to do maintenance on these systems. So quick overview about Inventus. Inventus Power, it's again, it's a global company. We are present in more than 10 countries. It's a US company with factories in US, in Mexico, in China, in Malaysia. We do basically lithium battery packs, custom packs, and also standard batteries for different applications, especially on the motive side. So we do batteries for the low-speed electrical vehicles, for heavy duty, for AGVs, drones, etc. We've been in the industry for more than 60 years. We have everything in-house. So we do design. We do have the BMS design, and also we develop the BMS in-house. So we also could test all our cells and our batteries in-house. We are approved by TÜV and by UL laboratories to perform testing. And last but not least, here you can see a couple of pictures of our batteries. And also for our custom batteries for different applications, such as, for instance, portable things, power tools, drillings, and vacuum cleaners, whatever. So I'm over the time, I think. So I only had 20 minutes, but yeah, I'm going to be available afterwards if there's any Q&A. And thank you very much for your attention. Muito obrigado. Boa tarde.
Thank you, Santi. Thank you, Santiago. And don't worry for the time. That was very interesting as well. So appreciate for your presentation and all the details. Again, coming from an industry player, yeah, from somebody who is manufacturing, working for a manufacturing company. Okay, there has been kind to share his experience with us today. So we continue now with engineer Joan Tarragó from Ferntech, which I introduced his experience in the first session. Joan is going to, again, thank you very much for being with us this afternoon, Joan, and he's going to share with us their experience in monitoring data collection and analysis for mini-grids. So thank you, Joan. The floor is yours. Again, try to keep to 20 minutes as much as possible. Thank you.
Okay, thanks a lot, Paul. I hope you can hear me. Yes? Can you hear me? No.
Yes.
Ah, okay.
Yes.
Okay,
Joan, go ahead.
Carlos, in the rooms in Mozambique, in Maputo. Thank you.
Okay, well, thanks a lot. I just wanted to make sure. Yeah, my name is Joan. I'm one of the co-founders of Ferntech. We are a rather small company that has been working in the last 4 years, almost 5 years now, developing solutions for remote monitoring and control of the centralized power systems or off-grid power systems. So we focus on mid-scale or small scale, always under the 1 megawatt peak type of systems in mainly 2 areas, mini grids for energy access and CNI, so commercial and industrial applications with special focus in Europe, Sub-Saharan Africa, and Southeast Asia. So today I'll just do a very brief and basic introduction of operation and maintenance concepts for PV plants. I will link this explanation to some digital tools out there in the market to help or to support these operation and maintenance tasks for mini grids or for off-grid power systems. And then I will mix this with a few concepts or considerations and steps in the end to take into account when it comes to the implementation of a monitoring system or monitoring technology in a system. All right, so I'll start right away then. So what's the purpose of having an operation and maintenance plan? Well, basically two main things, right? To keep the system up and running first, and then to as high as possible the performance ratio. So in the end, the goal is not only to keep the system running, but also to make all components of the system work optimally. So in order to keep the systems up and running and optimize the performance of the system with a good operation and maintenance plan, we basically need to put in place a good plan, which is normally divided in three types of maintenance: preventive maintenance, corrective maintenance, and predictive maintenance. So basically, as the name indicates, of course, the preventive maintenance is to prevent possible faults. And it's normally based on a number of tasks that we need to carry out to make sure that all parts in a system are up and running correctly. And among many tasks, the most important ones are a visual control of the solar panels and their mounting structure, having a visual and regular control of the cables and their power electronics, carry out a proper cleaning of the solar panels, measuring every now and then basic electrical parameters in important points in the system, basically current and voltage most of the times. And to do so, we have a set of different components, right, that can be used in order to carry out these preventive maintenance tasks. So here's just a list of some of the devices. So the first one, it's an IV curve measuring device, which is basically used to check the performance of the solar panels. The second one, it's an infrared camera. So that's helpful to, for example, detect defects in panels or the cells themselves in the panel. And nowadays, sometimes we can even find this type of infrared cameras installed in drones. So that's, of course, a new technology that starts to be a trend, especially for big systems. And then last, and probably the most important one, it's a simple multimeter, which is, very important to measure these electrical parameters in all these sensitive points of the system. When it comes to the corrective maintenance, so in order to optimize the performance of the system, we need to have, let's say, or we need to sort of react, so to say, when there is something that is going wrong. So we need to check which are the causes of the failure. We need to sort of see if that problem is in a system itself, on one of the components. So once that is happening, and if there are technicians on the field, it's important to go through normally a list of possible reasons that might have caused this failure, to therefore carry out a proper diagnostic and proceed with the repair. So for examples like this one, in order to diagnose what the problem is remotely, or to have a very straightforward list or action plan on what to do when this and that happens, it's highly recommended to start using digital tools so we can prevent those systems to happen, or to at least to be able to diagnose remotely what the cause could be and fix the problem remotely, or at least know what needs to be done. I'll explain a bit further later on that area. So last point, predictive maintenance. So of course, as the name indicates, so it's to foresee or to let's say, see a problem that might come or might occur in the future, and then to take action to avoid that failure to happen. A simple example could be to detect that a fan of the inverter is not working. Therefore, we know that in the future, the temperature of the inverter will go up, and then we should sort of do something to fix it before the system goes offline, because the inverter just it's overheated. Now, linked to some of the digital tools out there, that one in particular is for local maintenance. So there are very effective maintenance management software tools available. So, for example, when a problem occurs and there is something to be done, and we need to repair the fix the issue and know what the issue is, then scheduling maintenance tasks and systematically reporting the status of the system locally, it's something extremely important, especially if the skills of the local people is probably not very sort of deep. So companies like this one I'm showing here, 60 Hertz, they are from the US, and they have developed this maintenance software for local technician that could be totally run offline. And basically, it's a way to digitalize what we normally had in the past, like these long checklists of maintenance on operation tasks that need to be carried out by local operators. So these help to, as I said, create trouble tickets, to follow proceedings, to have a proper sort of data introduction locally when it's not possible to be done with a remote monitoring platform. So of course, when it comes to digital tools for remote maintenance, it's clear from our side that in order to carry out optimized, corrective, and predictive maintenance plan, it's really important to use digital tools for remote monitoring and control. So in a nutshell, as a summary, these type of tools can help us do things like remote monitoring to, for example, supervise the system performance and diagnose what the problem is. We can create or generate custom notifications in case there is a warning or error in the system or in one of the components. We can change the configuration remotely. And the idea now in the following slides is to go into a bit of more detail on all these steps and how the platforms like these ones work. So first of all, just a brief introduction of, in general, what the problem is when it comes to remote monitoring. So mini grids in general are complex, and it's not easy to get a complex system like a mini grid to run efficiently, and especially if they are in remote locations. So existing monitoring solutions can gather some information from one or two components, but do not give the whole picture of what is going on in the entire system. So optimization is definitely always required, and one thing actually is to collect data of one or two components, but it's very, very hard to have a real insight or knowledge about how the whole system is performing, especially when there is human factor involved, and you are an operator with hundreds of systems in your fleet. So basically, what we do at Ferntech is sort of close this loop and reach this optimization step that is necessary. And we do that by collecting real-time data into a local controller. And this controller runs algorithms according to what is required. So the idea is to collect the data from the whole system, analyze the data, create insights, and then make the system to take automated actions in order to optimize the overall system's performance. I'll explain some details of some of these steps, but first of all, let me just give you a roadmap that we normally have to consider when it comes to designing or implementing a monitoring solution. So we have designed, or we have stated that at least these 8 steps are necessary. I will not go through all of them, but I will just explain, or I will just go through basic concepts on some of the steps. So as you can see here, first of all, it's important to, once you're planning on installing a system, to have a plan, to know exactly what you want to do, whether what type of monitoring you want to implement, and plan it accordingly. And that starts with, the step number 2, which is identify what exactly is important to monitor for you, for your own application. The same applies for control. So what type of things you want to control, what do you want the system to decide automatically, what sort of automated processes optimization you would like to achieve with that system that you want to implement. Having that in mind, and also as part of the design process of the system, have proper device selection depending on what you want. Of course, not only the power electronics and the batteries are extremely important, also other devices that might affect the overall system performance. And I'm talking about sensors, I'm talking about modems, I'm talking about relays, even loads. So everything has to be taken into account, especially if you want to implement a monitoring platform that can collect data from everything. Of course, once you have decided all this, you have to sort of decide which technology to use, verify and test its functionality, and testing, especially when we talk about communication, it's a very, very important thing. As Pablo said, reliability, it's a big issue, especially in remote locations. So that step is extremely important in order to be sure that once we go on site, everything will be working properly. And of course, the last step is monitoring interfaces. So how you want to visualize the data, that's something also needs to be decided. So I'll start with this step number 2, which is identify what you want to monitor. Of course, there are some mini grids depending on how they are designed. Really, the amount of data you can gather, it's sometimes overwhelming. So it's important to take into account how you have designed the system, which parameters you want to sort of monitor. Sometimes from a battery, you don't need all the parameters from it, probably with the state of charge, and maybe critical values like temperature and voltage and other things will be enough. So going through the list of what exactly you want to log and show in the portal, it's important, or at least gives a really good sort of idea to the monitoring provider of what exactly you want to achieve. In our case at Ferntech, as I said before, we do data collection, data gathering from different assets or components of the mini grid. You have here some examples, but the idea is to collect the data locally from the devices themselves. So we connect directly to the communication port of the battery. We connect to the communication port of the inverter. Same with a sensor, solar sensor, or we can command relay output when we want to switch on or off a diesel generator or load. So basically, this data is collected through this little controller that we call UMC. And then this data is compressed and then sent to a cloud from which you can visualize the data from the portal. So that's the way it works. And data collection can be also done on the cloud through API, but I think I will talk about that a bit later. So in terms of compatibility, and that's something you also need to check with the monitoring supplier, and that relates to this device selection. So the batteries you decide on using, the inverter you decide on using, or the sensors, that will of course affect whether if it's feasible or not to monitor them all from one platform. That's one of Ferntech's core values, which is extensive compatibility with most of the major sort of off-grid suppliers in the market. You can see here different brands from power electronics all the way through diesel genset controllers, batteries, sensors, and other third-party technologies. When it comes to integration with third-party technologies, I would like to mention again 60 Hertz company, this local maintenance software that can be integrated with our platform, and that works via notifications. So for example, Ferntech platform can notify all the local technicians that some problem will occur or has occurred, and then can trigger sort of a ticket system to sort of create a maintenance list or corrective maintenance list that to be done and managed through a 60 Hertz platform. That's the concept. And the same applies with other technologies, the ones that you see in the left, SparkMeter and Stimaco. These are well-known brands for when it comes to the monitoring of the consumptions. So the monitoring of the energy meters that might be installed in every house of a mini grid. So this is a sort of the load consumption side of things that these two companies do, and the energy generation and storage monitoring side of things, which is what we are specialized on. These two platforms can be also integrated with one another. So you can, for example, make all the data flow to one or the other server. So that's important also to take into account when it comes to integrations and compatibility. Control. So the same as what you want to monitor, it's important to know what you want to control and how. So there are different types of controls. One control could be just changing a device configuration. So that's important to know that if there is a problem with an inverter and or the battery, and it's all about changing the config parameter of that device itself, that's one level of control. Another one is, look, I just want a control algorithm to run at a specific speed, and that's also important to know, what sort of control algorithm you want to implement and how quick should it be. And at Ferntech, we do rather long or rather slow sort of control, set point control, which I will explain an example later. But if you want a quick, for example, quick response control, you have to use devices like the ones I'm showing you in the screen. So very fast millisecond response times is what normally you do with typical PLC-based solutions, like as you can see here, Siemens or DeepC. These are of course faster, but of course more expensive. At Ferntech, basically, we have implemented a list of sort of control algorithms. Basically, the idea is to convert passive systems into closed-loop smart power systems. So we have a growing portfolio of standardized algorithms that could be from automatically start or stop a diesel generator, depending on the state of charge of the battery. That could be, the control of a water pump, as you can see here in the screen. That's just a very simple example, but quite useful. So it's about turning on or off a water pump when, for example, the state of charge of the battery is very high. So it's a good example as a deferrable load. Well, that's probably the most important step, one of the most important, which is once I know what to monitor, what to control, and I want to select the devices, well, it's all about making things communicate with each other, right? So communication protocols, it's one of the things that normally takes more time to check, double check, and test. So in our case at Ferntech, we use that controller most of the times, which has this amount of communication ports. As you can see, these can really cover almost all different scenarios that you can find in a mini grid. And in case we need more inputs, outputs, we can always add some more controllers in parallel. And the same applies with devices. So it needs to be taken into account the way all the devices communicate. And you can see here some examples of inverters, SMA, Voltronics, Infinite Solar, or the diesel generator, or just a simple energy meter. It's important to, once you buy or select a system, to coordinate with a monitoring supplier to double check that it has the proper communication protocol. Same applies with accessories. So sometimes it's needed to have some sort of communication gateway to make a controller communicate with the device. These are just some examples. Sometimes you need an Ethernet switch. Sometimes you need, for example, as Pablo mentioned before, XOM CAN to convert the CAN signal to the internal proprietary communication bus from Studer. So that's something also very important to take into account. Well, now I'm going a bit into quite a lot of detail, but it's all about the same. So when it comes to communication protocols, make sure that it has the communication interface, how things will be connected to each other, especially in rather complex mini grids, and whether if you have or not the information of the communication protocol, because sometimes a new device needs to be added. And in order to do that, the supplier of the monitoring solution will need all the information. And that includes also the list of all how to read the registers from the communication protocol. Well, as I mentioned before, communication can be physical, locally through a cable, but sometimes could be also through the cloud. So what we call API, it's a way to get data from a device, but not from the site, not from the device sitting locally, but from the cloud. We get the data from the web server of this other manufacturer. So just so you know that this is also start to be quite typical in monitoring providers. Very important step, and I'm now one of the last ones slides, I think. Communication equipment. Of course, if we have everything connected, but data cannot be sent to the cloud, of course, we have the system offline and we cannot see anything. So internet connectivity, it's normally done through GSM modem or satellite. As I said, sometimes accessories are needed, like Ethernet switches, some Ethernet breaches, etc., etc. Satellite communication, it's now way cheaper than it was years ago, so it's something that starts to be common. But you need to check, and that's very important, the speed that the monitoring provider needs. It's different to monitor at 2G with an area with weak coverage at an other area that it knows it needs higher speed or a large volume of data. So that's really, really important. At Ferntech side of things, with a 2G connection at 50 kilobytes per second, it's sufficient for the controller to send data to the cloud because we do massive data compression. And also thanks to that, we can save quite a lot of money on when it comes to the data transmission. So an average mini grid will not need more than 100 or 200 megabytes per month as a contract for the SIM card. So just to finish, monitoring interfaces, you can, of course, read the data through the web server on a platform, on a website from your laptop, but you might also need local access to some data in case internet is not working or in case you have a local technician. So that's also something to take into account. You can have solutions in the market like Victron with their famous color controller. And we have now developed an app that runs in Android that can be installed in a tablet that give access to a sort of local data visualization when the internet is down. So that's it. Thanks for listening. I'm happy to answer any question now or later. Thanks a lot.
Okay, thank you very much, Juan, Engineer Juan. This is really, really interesting part of the mini grids, not only the mini grids, but all the PV systems, yes, because we make a lot of effort in designing PV systems. We pay a lot of money to invest in PV systems, to install them, and then sometimes after 1 month, we don't even know how these systems are working. And we cannot, if we are EDM or FUNAI or, we cannot afford to go all the time to these remote locations to see how things are going. So monitoring systems are very, very, very useful to know if systems are working and how are they working, okay? Also for grid connected applications where very possibly we have financial mechanisms, we have project financial, we have loans, we have performances to guarantee. And if we don't really anticipate misperformance or underperformance, we can have serious trouble, in the midterm, long term, or even in the short term. So let's be aware that monitoring systems are relatively cheap if we compare to the overall cost of a PV system, but they are really, really, really helpful, okay? So I really appreciate the time that Engineer Joan has spared with us this afternoon to share their tremendous experience. You can see flexibility is essential for monitoring. They need to communicate with many, many components and to offer facilities and to offer all the project developers and operators as many tools to take proper decisions, Okay, so thank you. Now we're going to start with the final part of today's session, where we're going to look at some more mini-grids examples, okay? Sim. We are going we are going to explore, yeah, some mini grid examples, and our guest speakers, engineer Joan Tarragó and engineer Pablo Muñoz, engineer Santiago Antolin will comment, yeah, on the different case studies, each one from his point of expertise. Okay, so please, engineer Joan, the floor is yours. Thank you.
Thank you, Paul. I will just go through some use cases that we did. I know the idea is to dive in one of them, especially. I also have some live data that I can show in the portal of 2 other mini-grid cases in Africa, in case there is time for that and you find it interesting. So well, basically, that's the idea here. So in this first slide, what you see, it's some of the projects that we have implemented in different continents. We have around 300 systems online, and our approach is always to not going to on-site. So any support, any the deployment of the system, everything could be remotely, and the idea is to do it in a very user-friendly way, so the user or the operator can deploy it without any support from our side. So that's the concept. I will just go through some examples. As I said, we will dive in especially in one if we have time in others too. And the first one we will go into a bit more detail is this mini grid in Mali. Actually, there are 4 mini grids in Mali that has been installed. All of them are the same, and it's an energy access type of system. So the goal here is to provide electricity to a mini grid, to a village. And the highlight here, or the special case on that system, it's the mix and match of different brands existing in the market, SMA, for example, and Studer, and also the architecture of how the system was designed, mixing the AC and DC coupling in the system. So we will go into more details there, but just to give you a bit of basic information of the system. So the customer, in that sense, in that case, it's a foundation from the Netherlands. And by the way, they were happy to share that information and disclosure who the customer is and who paid for the technology. Actually, in that system, or these 4 systems in Mali, were co-financed by the European Commission. So there is no problem in that sense to share this information. The customer is a foundation called FRES from the Netherlands. It's a small nonprofit multinational founded in 2004 in the Netherlands. And basically their goal is to provide off-grid solar energy in some African countries, especially Mali, Burkina Faso, Guinea-Bissau, and Uganda. They focus on small systems for solar, like solar home systems. They do mini grids, and the goal is also to focus on multifunctional mini grids, meaning mini grids that can not only supply energy to a village, but also supply energy for productive use of energy, meaning some little industry or some, I don't know, ice machine, or for irrigation purposes, so for agriculture. So that's the goal of the foundation in those mini grids. On that system in Mali in particular, that's a very high level, simple design, and Pablo and Santi also will go into more details on the why and the what on that system and why it was designed like this. Maybe what I can only say is that it's a system that it's, as you can see in the picture, DC coupled. So the panels are connected, are charging the battery through a DC-DC converter from Studer, and then an SMA inverter is used to convert this energy from the battery from DC to AC. There is also a diesel genset connected, and the particularity of this system is that they decided also to add an AC coupled PV system. In that sense, in that case, it's a set of panels connected to Sunny tri-power grid type inverter from SMA. So that makes this system a bit particular, right? Mixing this AC and DC sort of a design when it comes to the power schemes. So these are the very high level specs. So this mini grid, and I think it's the same for the all the 4 mini grids in Mali. So it's a 80 kilowatt peak PV solar array. You will now see a few pictures. For that mini grid, a powerhouse was needed to be built, and the powerhouse was housing not only the inverters and the power electronics, also of course the battery that's working at 48 volts DC, and they have a nominal power of 700 kilowatt hours. So again, Santi here can give more details on why the design of all this. And as you can see here, the design covers a 30% versus a 70% AC architecture to provide a robust design. So, well, as I said, this mini grid, the idea of this mini grid and the others that Press Foundation implements is to provide electricity to a community. Well, that one in particular had community centers, mosques, churches, and some artisanal workshops. I have to say, and that happens relatively often, we do not have much live data to show, because as what happened many times in those mini grids, the investment is done, the mini grid is installed, but the connection to the village, for whatever reason, it's not done yet. So there are either no load, so no consumption, or very, very low. What sometimes happens as well is that because of lack of local management, there is no, or lack of planning, there is no data connectivity, because the SIM card needs to be reloaded or topped up. And that's one of the reasons why sometimes the system, even if we know it's working, it's offline. We can just do local monitoring, but not remote. So these type of problems happen. And in that case in particular, I cannot show the real status of right now of how the mini grid is working. These are just some pictures of the mini grid itself. So it's in this little village close to Bamako. You can see here the powerhouse that was built for that mini grid. They built some fences around the PV yield, and well, here one of the operation and maintenance sort of local responsibles, measuring voltage and current with this multimeter that we mentioned before. Here the whole battery packs. You can see here the SMA inverters. Yeah. Here's some more details on the technology itself. So you can see here the mix of the two technologies, Studer and SMA, and Pablo can give more details, but these little devices you see here in the middle are also devices from Studer that allow local monitoring and local configuration of the devices. So yeah, that's sort of the pictures of the status of the mini grid today. These pictures are quite up to date, and this is what the user see in Ferntech platform. So what you see here is what we call layout diagram. So it's a picture actually that can be designed and customized according to the needs. In that case, the customer prefers to see this single wire diagram where you can see all the devices. You can see, you know, the values, real-time values of the batteries, the consumption or the power going through the components. And you can see things like also like this. So how many devices are connected to, in that case, to the Ferntech monitoring platform. So you see here the mix of different SMA components, the Studer components. There is a modem here from a brand called Teltonica. Yeah, so there is a solar sensor as well, it's that one here. So you can see here, in that case, which devices are in the mini grid. And actually, that's a bit of a special system because we had to use 3 controllers instead of 1 because we needed 3 CAN ports. Yeah, that's basically it. I don't know if probably Paul, you want to intervene here.
Yes. Yes, thank you very much, Joan. If we can go back a little bit, some slides. Yeah, okay, here exactly. In here, we can see the architecture, yeah, of this mini grid, yes. I would like, Pablo, if you can please tell us a little bit why a mini grid like this is considering this mixed architecture of DC coupling and then after adding AC coupling. Why did they do that? Because it's a little bit, yeah, it's a little bit particular, right? And also we can see here at the bottom we have a combination of different brands. Yes, we can see Studer for the charge controller, then batteries, and then SMA for the inverters. We see two types of manufacturer for power conditioning. How is this compatible? Is this possible? Is this working well? What is your opinion on this configuration?
So yeah, it's a very interesting project because in fact, the fact of hybridizing DC and AC coupling, it allows to take the advantage of each of the architectures. So as I can see here, the DC coupling, solar DC coupling is interesting and is important because, well, the system is purely off-grid. So the batteries should be always be charged. So imagine there is a blackout and the yellow inverter from SMA shuts down because there is a problem. The next day, when the sun is coming back, through the solar charge controller on DC, the battery will be charged again. And then when the battery is charged, the SMA inverter can start again and run the system as it was. This is what they call the black start. So this is an interesting feature of the DC coupling. As well, the solar directly connected to the battery allows to make sure that even if the loads are big, the battery is always fed with solar energy during the day. The fact of adding AC coupled solar structure, I will say, is mostly due to the load profile. So in this case, the load profile will have a heavily daily consumption, and the AC coupling allows also to use the AC coupled PV production during the day to be used directly on the loads, and then the DC coupling solar production will be kept for the battery to be charged. Is this kind of mixing that is interesting.
So Joan, can you sorry, Pablo, can you exactly, thanks. Aha.
Yeah. So in this case, we mix. The percentages, I think, well, they have a bigger amount of AC coupling here. So I guess this is because the load is mostly daily balance. So there is a lot of consumption during the day. We thought in my presentation before the comparison in terms of efficiency, but in both cases the efficiency is still high. So what will mean? So what will be the difference? For me, this architecture is the most efficient one in terms of cost as well, because this means that we take advantage. We are more efficient with the AC and the DC at both sides whenever it is required. So we need 80 kilowatts of PV. If we have built this purely on AC coupling, we might probably need it to have maybe 85 kilowatts to compensate the fact of loss of efficiency for charging the batteries. If we build everything 100% on DC coupling, the same. We need to compensate with more solar in order to compensate for the efficiency on the daily consumption. So it's very important. The mix of two different providers or technologies or manufacturers is not an issue in this case because the battery is always the interface between them, as you can see. And all the technology, battery inverters, solar charge controller, they do the regulation based on battery voltage. So every device will measure the battery and will adapt to what each one is seeing on the battery. So it's perfectly compatible. Even through AC coupling, you can charge the battery. And the only problem that we will have in these cases is that every manufacturer will have its own communication platform between its own devices. So Studer will not communicate directly with SMA. SMA will not communicate directly with Studer in order to monitor, to control. This is done, in this case, through Ferntech that can read from Studer and from SMA. And the problem is solved. And then Ferntech is able also to aggregate all the, for example, solar production, just to calculate how much was on AC, how much was on DC, if we want to have the general number. So for me, very interesting architecture and very recommendable for adapting really to the loads, to the demand.
Oh, thank you, Pablo. I think then what we can learn from this example is that understanding the demand, understanding the load that's going to happen, it's very important. And before we design the system, we really need to take time, yes, to understand the demand. And not only the demand in the first years of operation, but what can happen afterwards. Yes, so the demand has to be really the starting point of our mini grid projects. Okay, I think this is important, ladies and gentlemen in the room. Yeah, for those of us that will be working, are working in the design and the development of mini grids. Yes, to understand the importance of demand analysis in detail. Because from this example, we can learn that there is a mixed configuration of DC coupling, AC coupling, combining different technologies, different manufacturers, so that we can optimize a complex system like this. Okay, one question for Santi, for engineer Santi, please. We see here a battery bank, okay?
Yes.
With 772 kilowatts. Can you tell us what type of battery is this one, and why did they size it like this, please?
Okay, well, in regards of what battery type it is, and actually, Joan, if you can go to slide number 9, where we have better pictures, we will be able to see that this is this is a transparent case, so we can see the liquid electrolyte in the battery cell. So this is a fluted battery, all right? And actually you can see as well, there is some caps on top of the batteries. These are really huge cells. So you can see the caps on the top of the battery. That means that this is a fluted battery. We need to top up with distilled water these batteries regularly. So this is what we call OPZS. It's a tubular plate type of battery. And yeah, the sizing. I mean, you actually you are completely right, Paul. That you really need to have an exhaust survey of what the load is going to be in order to size not only the PV panels, the PV blocks, let's say, but also the battery size. So the battery is actually probably it's the most expensive component in the system. So you don't want to oversize a battery system, because otherwise it's going to be super costly. So you really need to have a very detailed and a very you really need to know what's going to be the future demand in order to correctly size the battery. So it's 772 kilowatt hour nominal capacity of the battery. That means that because it's a fluted battery, it's a fluted lead acid battery. In order to have a maximum lifetime of that battery, you're going to be using half of it, so 50% of discharge. So this leads us to 380 kilowatt hour usable energy. And if we take out as well inefficiencies from the battery, but also from the power conversion equipment, we end up in around 310 kilowatt hour usable energy. So imagine you bought a huge battery bank of 772, but as usable, you are gonna be only using 300 kilowatt hour. So yeah, this is also to take into account and to take into account when designing and when sizing a battery. So for instance, if you would be in the position to maybe use lithium batteries, you probably can discharge deeper the lithium batteries, so you don't need as much as buffer, all right, on the sizing system. So just also to take into account. The other thing is the transportation. So we are talking about 700 kilowatt hour. If we take around 30 watt hour per kilogram, this huge battery bank weighs around 25 tons. So it's an amazing.
Are you saying that all we can see here is 25 tons of battery?
Yeah, I don't know exactly. I don't know, but it's a huge battery bank. So I see it's how many banks? It's 1, 2, 3, 4, 5, 6, 7 banks. So it is a huge one. So so I mean the battery room looks pretty good. So looks clean and tight. There is some proper ventilation, but it's huge. So also we have to take into account these things. No, if you would be using lithium batteries, maybe because of the high specific energy, you can reduce the battery room. Probably you don't need as high ceilings as this one for proper ventilation. You are also reducing cabling costs because you don't have as much as battery banks as here. So yeah, it's all in the process of when designing the battery bank and the whole complete system. No?
So perhaps one idea that it occurs to me is that this design obviously is very good, very excellent for a one-off project, like a pilot project. But if we are trying to do a program of tens or hundreds of mini grids, yes, probably the costs of what you are saying, yeah, the civil costs, the construction costs of the technical room, the transportation costs, yes, of 25 or 20 tons of battery banks for one mini grid. All of this in a mini grid program like the ones we can design in Mozambique. All these things will be factors that need to be evaluated, right?
Yeah, absolutely. And not only during installation, so also during maintenance. Ferntech in this case, it's going to help a lot on the maintenance, but at the end there should be someone there doing the maintenance, so cleaning the batteries, topping up with distilled water, cleaning the terminals for corrosion, checking specific gravities, specific temperatures as well. So this adds it's an added cost to the complexity of the project itself, no?
Yeah.
And so yeah, I mean it's a good pilot project. In terms of battery, I would probably use other options.
Yeah.
Okay, thank you.
If I may add, Paul, I mean, you guys are totally right when it comes to improving the design on these mini grids, especially when it comes to scaling up and do not only 2 or 3 pilots, but do 50 or 100, right? So it's really, really important to, once first design is decided, then you have enough data to analyze, well, was the design oversized or undersized? Should be the battery bigger or smaller? Should be lithium? Or so these analysis that needs to be carried out, and again, that's why digital tools are so important, are the ones that will help on deciding how to optimize the system and for example, reduce the investment costs for the following mini grids after implementing the pilot. So that's extremely important. I also wanted to mention one thing. We talked a lot about measuring the load curve, which is very important. So when it comes to measuring the load in an existing village, there are some devices out there that are really, really useful. And I just wanted to mention one because it's the one I know, if you don't mind, but it's devices like this one. Let me just share here. Devices like this one, in that case, is this brand from Spain. This is a energy meter or power meter that can be temporarily installed in a site. For example, the means or the power supply on a village, and then you can detect the load, what the load curve is, and then you can see the data in the portal, and then you move on and you use the same device in another village. So devices like these ones are really, really interesting.
Yes, thank you. This is a very good suggestion that when we design mini grids, we can use we can learn from the demand in other similar villages that have already a mini grid or the grid, and we can take this data to generate the profiles, yes, if necessary. Can you go back to number 10 slide, the previous one, I think? Yes, the next. This. Yes, Pablo, please, in the top left picture, we can see some, apart from the charge controllers from Studer, we can see two equipment there. Can you perhaps, Joan, show? Look like monitoring equipment. Pablo, please, engineer Pablo, can you tell us what is this?
Yeah, so this is the one on the bottom, the gray one, the light gray one, is our remote control, configuration control. This is the main interface with the devices. So it's the way a user can go into the configuration of the devices and can check what is the parameters. As I was saying before, for example, this is where with this one, we will configure exactly the charging profile of the battery, what is the maximum current that the battery should be charging, what is the absorption voltage, floating voltage, and so on. And it has also a data logger function with an SD card inside, where there will be a log file of the data coming from the devices store for every day. So it will also do a local data logging of the system. If, for example, the Fairtech device is not communicating or has a communication problem, through this SD card, we can have some of the data from Studer that you should later on work with. The second one is actually communication bridge. As Joan was mentioning before, this is it's connected. The black cable that goes to the bottom, is connected to the charge controller, to the charge controller 1 and the charge controller 2. So it goes into the Studer communication bus. This is a Studer proprietary protocol communication. So this is between a Studer and only a spoken Studer. Then the white cable that goes above will go to the controller from Fairtech, and then is this cable that allows the communication between the Fairtech controller to the Studer devices. So it's through this cable and this communication bridge that the communication will be established, and Fairtech can read and write into the Studer protocol.
So thank you, Pablo. So what we can see here is that even if the remote monitoring system at the moment is not working, is not sending data, even though it is installed, the remote monitoring, Joan cannot see the data from his office in Germany, but you are telling us that the data is actually being stored there in these devices. So the data is not lost, it's just that it is there, and to check it, we need to go to Mali, correct?
Yes, we need to go to Mali, and then you will need to go to Mali to take the data from Studer in this, and then the data from SMA in the data logger from SMA and then work with them all together.
So this is, thank you, Pablo.
But,
So
yeah.
Sorry, you want to add something?
No, it's everything.
I just wanted to mention that local storage, it's done in this Studer device for Studer components. Local storage of data, it's also done in the controller device for all the components. So in that case, this data is being logged and saved locally in Mali from all the components. And yeah, the solutions like this local display are the ones that are needed when there is no internet connectivity.
Yeah, just to add, sorry, I didn't mention, but this communication bridge, what is also interesting, is not only for reading, it's not only for monitoring, it's also for control. So it gives you total access to the Studer devices configuration and so on. So from the controller from Ferntech remotely, you can configure and change whatever you need to be changing, any parameter that you need to adapt. And this is why monitoring is also important, because with the data that you have collected, maybe you can correct or adjust the configuration.
Okay. Okay, thank you. Joan, perhaps we can look at another example where you have data, just one, the one you prefer.
Yeah, I can show, I have two examples, one in Congo and one in Nigeria. Maybe one it's DC coupled and the other one it's AC coupled. So maybe it's interesting to check the other one because that one in Congo, it's, as you can see here, basically using Victron components. And this is just a screenshot of data just taken a few days ago. But maybe we can focus on that one here in Nigeria. That's a mini grid that we collaborated with our partner in Nigeria called IoTech. And this mini grid powers an entire village that it's called Mokoloki. And actually, this village was in the media a few weeks ago as it was sort of in the news because it's one of what they say, one of the first undergrid mini-grid projects. Basically, undergrid, it's a new concept of mini-grids that will be connected or are connected to the grid. So they are not, or they will be not entirely off-grid, but it's a mini-grid that sort of can offer end of the line services to the grid company.
Hello?
Yeah.
Yes, hello.
Yeah. Boa tarde mais uma vez. Queria perceber um pouquinho do slide anterior sobre o data. Slide 10.
Aqui?
Sobre o data.
Esta?
Sim, sim. Sim, o anterior. Sobre o data. Não sei se temos a aplicação e não sei se podemos ter as características do data log.
Sí, las características del data logger.
Sim, sim. É que temos usado também esse tipo de inversores. Temos tido alguns problemas porque eles não apresentam o display agora.
Claro.
Não sei se podemos ter as características e...
Sí, thank you for the question. What we can do while Joan presents the data on Nigeria, Pablo, if you can open the specs of the data logger, and then you can eventually share that. Yes.
Okay.
So we are going to prepare the answer for that now. Yeah, the colleague. Engineer Pablo will prepare that in a couple of minutes. He will explain to you. Okay.
Thank you.
Thank you.
All right. So this mini grid in Nigeria, it's an AC coupled system with, as you can see here, basically using SMA systems only. So these blue inverters are grid connected power PV inverters. And then there are Sunny Islands, also SMA, so, bidirectional inverters that are installed connected into two battery banks. And what I will do is just to show real data of that system, so live data of that system. Let me just update.
Now you're now going to connect live, yeah?
Yeah. Can you see the screen?
Yeah.
Okay. So yeah, that's live data right now. So this system in Nigeria, as you can see here, it's nowadays at this very moment charging the battery at 10 kilowatts and around 5 kilowatts in these two battery banks. We can see here all the PV strings generating more or less the same amount of energy, which of course is the way it should be. Otherwise, we could see then here very easily that maybe some of the PV panels are dirty and some others are not, if we see big differences between the PV strings. In that system here, actually, it will be upgraded soon because there is no measurement of the load. But soon we will put an energy meter and soon we will connect the controller to the diesel generator. So we will implement control algorithms to optimize the diesel genset a bit better. But what I can show, oops, okay, second. Yeah, what I can show is data of the system itself. So basically what we call the dashboard of the system, it has different parts. It's always the same structure. So layout diagram where we show real data. And then these little boxes are KPIs. So basically our key performance indicators where can give an overview of the values that are important, and in that case, well, it's about state of charge, it's about power output, and it's about the location of the system. It's actually, as you can see here, not far from Lagos, and then some graphs. And as I said during my presentation, the graphs can be customized, and basically what we can see here, it's let me just go to that screen. So this graph shows the output power of the inverters. So in other words, these graphs can indicate the power consumption of the grid, of the mini grid. So basically what we can see very quickly is that during the daytime, so during the morning and afternoon, the consumption, it's not very high. But then the consumption starts to be high during the evening. So here's one of the things we can say. Well, this mini grid, even if it's AC coupled, the load profile, so the most part of the loads are actually at night. That could be, so the loads are not very high. We're talking about 10 kilowatts. That makes me think that although the mini grid is working and connected, the loads that will be basically connected during the day, that most of them will be loads for, from some little businesses coming from these appliances. These appliances have not been connected yet because the loads during the day are really not very high. And there are some little peaks here and there, but in general, the consumption during the day is not very high. So what makes this behavior to the mini grid? So, well, as you can see here in the curve of the state of charge, of course, the state of charge of the battery increases during the day because it's sunny. But then once the people start using the loads in the afternoon or in the evening, the state of charge goes down, goes down, goes down.
Yes.
So at some point, because it goes below a certain trigger value, what they do is to connect the diesel generator. So, so that's why you see these peaks here, these peaks of the state of charge of the battery. But it's much easier to see in this graph here. So as you can see here, the diesel generator was connected here at 10 p.m. And that's why we can see here a big jump of energy coming into the battery. And then the diesel generator stopped at about midnight, but the consumption was still relatively high until, I don't know, 3 a.m. And they disconnected the diesel genset again at 4 a.m. So this is a good example on a not very optimized mini grid, because switching on a diesel genset at 1 or 3 a.m. it's definitely not ideal. So this is what we want to implement now as a next step, to automate and have automatic scheduling of the diesel genset for those on and off, so we can treat the battery a bit better than it's treated right now. So, well, that's an example of data being checked up to today, and you can see in other slides, in other parts of the portal, all the components connected, and you can diagnose problems on, for example, look, I know this parameter or this device failed, and I want to know when and why. So these graphs gives information on which devices failed, and you can sort of go into more detail on the error messages. So a lot of technical information, but I think it's a good sort of overview of what sort of things you can see in a live.
That's really super. So you can see from your office in Germany, in Berlin, what's going on in the mini grid in Nigeria at the moment. You can see everything.
I can do that. And for example, if I see that there is an issue with an inverter, I can dive into really a lot of details. So the dashboard I'm showing you, it's the dashboard showing data just from one inverter. It's one of the Sunny Islands. And these dashboards are created automatically. So again, a bunch of graphs and things. But for example, if you know that an issue is there and you want to change one configuration parameter of that device because you know that will fix the problem, then you would go into this screen called configuration. And you can see here a long list of parameters that, in that case, the SMA devices offer to the operator to change. So you would then go here, click, and change the parameter. And well, that's super useful because many times just by changing a parameter can literally save a trip to site. So saving a lot of money, a lot of time.
Of course. Thank you very much. I think it is now time to open the floor.
Let me share my screen.
Oh, yes. Sorry, Pablo, for the gentleman's question. Yes, sorry.
Yes.
The gentleman in room, room 01.
So you can see, so and it's quite relevant with what Joan was saying. All the data that he was displaying remotely is also available locally. And this is the content of the SD card. So it has a lot of folders on it with the configuration, with the software firmware updates, if they are required, and then CSV files. So the question was which type of log files was. So we work with CSV that can be standard CSV files. We have in the remote control, we have the configuration files of every device. We have files with all the errors or messages from the systems and all the log files. And the log files are stored one per day. So at midnight, automatically, one file is created and stored in the SD card. Okay. With those log files, we can use an Excel, for example, tool. We have this tool available free in our website, and then you can just load the data and see also all the graphs from the system. Okay, and just for you to know, if you want more detail, measurement resolution is 1 point every minute in this specific log file. So as you can see, I will say local monitoring for the manufacturer itself is like this and quite robust. Then we have also remote monitoring from manufacturers. So for example, it's also possible to remotely control and monitor the student devices. Then with Ferntel controller, we will have local information stored, and then the remote information aggregated in a higher way. And then, for example, with Ferntech, I guess what you can do is if you need more than 1 point every minute, you can configure and go more advanced in this kind of functionalities. Right, Joan?
Yeah, that's correct. We read, the controller reads from all the devices as quick as the controller and the devices can. So for example, SMA gives an answer every 3-4 seconds, so it's relatively slow. Other devices like lithium batteries can be really fast every second. So basically, we monitor, we can do monitoring up to 1 second. So it's really high accuracy. And then this data is collected, and then we also measure minimum and max. So if you do averages of 60 seconds or 5 minutes, you can also check what the minimum maximum was. So you can diagnose much better when something was wrong, because sometimes you have peaks of voltage or current. So yeah, higher data accuracy is of course one of the things we believe it's important, and that's why we implemented this architecture.
Okay, thank you. Are there
I hope this was answering the question.
Yes. Are there any more questions in the room 1 or room 2, or any comments? We can have a bit of debate if you want. We have still another 10-15 minutes. Dr. Lucas.
Yes.
It is time for questions. Please take the opportunity. We have these 3 industry guest speakers that have shared a lot of things with us. If there's any question, any doubt.
Ok. Alguma pergunta, algum comentário, colegas? Alguma pergunta, algum comentário?
No, everything's all right at the room.
It's also un poco tarde, ¿no? Ya están cansados.
Yeah, Paul, no question.
Okay. You have the materials of the talks have been shared, also with the contacts of the 3 gentlemen we have here. I think they will be happy to receive any questions or request for further information from anybody. Again, if anybody has a doubt or something that would like to ask them, but before asking them, if they want to check with me, I'm also happy, yeah? And I can also facilitate the consultation with Engineer Joan, Engineer Pablo, and Engineer Santiago if necessary, okay? If you haven't understood everything, or if there was something that was very new to you, don't worry, we have another 9 sessions in front of us from now until February. Many of the things that were explained today, we will be repeating, we will be using them, yeah, for the sizing examples and for the other sessions we will have in this course. So don't worry if there was something you didn't understand completely. You can always bring it back to me in the next session or the following sessions about batteries, about inverters, about charge controllers, about monitoring, and then we will deal with it in the following sessions of this course, okay? So if we can give a good thanks to the 3 invited guests speakers today. I think it was wonderful that you could share 3 hours with us today, and I hope everybody has a good rest of the day, good evening, stay safe, and we continue with the course tomorrow with the session. Bart, is it tomorrow we start with hydro or with biomass?
We start with hydro, and then the afternoon is a biomass session. Combustion.
Okay.
Yeah.
Okay, so I think we can close here unless anybody has any other final remark.
Okay, I think we can close. So
thank you for your time.
Pardon me?
Thank you for your time.
Thank you very much.